As our understanding of aging shifts from chronological age to biological age, researchers are increasingly focused on finding precise molecular indicators that reveal how well, or how poorly, the body is aging at the cellular level. Among the most promising frontiers in this effort is vascular health, which plays a central role in determining lifespan and health span alike. Emerging biomarkers such as peptidoglycine alpha-amidating monooxygenase, PAM, and bioactive adrenomedullin, BioADM, are now being studied for their ability to reflect the state of the vascular system in real time, offering potential as both diagnostic tools and therapeutic targets. These molecules are helping scientists uncover how blood vessels age and why maintaining their integrity may be key to living longer, healthier lives. Vascular aging is more than just stiffening arteries or higher blood pressure. It's a process deeply intertwined with inflammation, endothelial dysfunction, and impaired regulation of blood flow and barrier function. As the vasculature deteriorates, oxygen and nutrients are less efficiently delivered to tissues, waste products accumulate, and organs from the brain to the kidneys become increasingly vulnerable. Understanding how to monitor and intervene in this process has long been a challenge, but new discoveries in molecular biology are beginning to illuminate a path forward. PAM is an enzyme involved in the biosynthesis of numerous bioactive peptides, many of which regulate cardiovascular and neuroendocrine functions. Recent studies have shown that PAM levels correlate with vascular integrity and endothelial health. Because PM plays a role in the amidation of peptides, essential for their activation, it indirectly influences the signaling pathways that modulate vascular tone, inflammation, and repair. Lower PM activity has been linked to impaired endothelial function and increased vascular leakage, both hallmarks of aging vessels. What makes PAM especially compelling is its presence in circulating plasma, making it accessible for non-invasive testing. Even more directly associated with vascular health is bioADM, a stable and active form of adrenomedullin, a peptide hormone that plays a critical role in maintaining endothelial barrier function and blood vessel integrity. Originally identified for its role in vasodilation and fluid balance, bioADM is now being recognized as a dynamic responder to vascular stress. High levels of bioADM are observed in conditions like sepsis and heart failure, where the endothelial barrier is under acute threat. However, researchers are also finding that moderate elevations of bioADM in otherwise healthy individuals may indicate subtle, early-stage vascular dysfunction, making it a candidate biomarker for detecting accelerated vascular aging before clinical symptoms appear. Recent research has started to link variations in PAM and bioADM levels with age-related diseases and frailty. In population-based studies, individuals with more favorable PAM and bioADM profiles tend to have better cardiovascular resilience, lower inflammation, and reduced incidence of ischemic events. These markers also correlate with other signs of healthy aging, such as preserved kidney function, robust physical performance, and lower rates of hospitalization in the elderly. Importantly, because both PAM and bioADM reflect vascular function across multiple organs, they may offer a broader view of biological age than markers confined to a single system. What's particularly exciting is the possibility of using these biomarkers not just as indicators, but as therapeutic guides. In preclinical models, drugs or lifestyle interventions that improve endothelial health, such as aerobic exercise, Mediterranean-style diets, and caloric restriction, also appear to normalize PAM and bioADM levels. This suggests that monitoring these biomarkers could help evaluate the effectiveness of anti-aging interventions and personalized strategies based on individual vascular biology. It also raises the prospect of directly targeting the adrenomedullin signaling pathway as a therapeutic avenue to delay vascular decline. Pharmaceutical research is now exploring compounds that modulate adrenomedullin activity or enhance PAM function, with the goal of stabilizing the vascular barrier, reducing systemic inflammation, and preserving organ perfusion in aging populations. Early trials are focused on high-risk groups, such as older adults with cardiovascular disease or early signs of frailty, but the long-term vision is broader, to develop preventive treatments that help maintain youthful vascular function across the lifespan. These developments also support a growing shift in longevity science, away from treating individual diseases in isolation and toward preserving the systems that sustain overall physiological resilience. The vasculature, as a central conduit between the brain, heart, kidneys, muscles, and immune system, is increasingly viewed as a master regulator of aging. PAM and bioADM may well be the molecular messengers that allow us to monitor that system in fine detail and intervene before irreversible decline sets in. In this context, the promise of biomarkers like PAM and bioADM is not just in tracking disease, but in forecasting vitality. They offer a lens into how aging unfolds at the level of endothelial cells and microvascular networks, places that are often invisible until breakdown occurs. By identifying these subtle shifts earlier and with greater accuracy, medicine moves closer to a truly preventive model of aging, one that doesn't just treat illness but cultivates health from the inside out. Ultimately, the discovery and application of PAM and bioADM reflect the broader promise of precision aging science. They remind us that the future of longevity may depend not on adding years at the end of life, but on protecting the circulatory foundation that sustains every moment of it.